Yeah, I decided actually to shift a little bit or to walk away a little bit from the schedule which is announced on the web page. So the idea was to have some special features of the flash code which I will talk on Friday, so on the last day, and I shifted everything by 1 day essentially. So today we will talk about the gravity modules. But before this, I want to make a few comments because there were a couple of questions yesterday. First of all, one thing concerning the manual, the user manual, the flash manual. So the tar file which I provided you contains also a manual which has the same name, namely flash4_UG for user guide .pdf. But this contains only a small fraction, or actually an additional part to the manual concerning particles and sync particles. So if you look up this manual, this has only 40 pages compared to the one I announced with 500 pages. So I copied the SIG manual in my PFS folder, and you can download it from there. So this is about the manual. And there were also questions about the number of refinement levels you can use for the flash code, and so meaning to what kind of resolution you can go. And essentially there's no real limit. I think there's a hard limit of the order of about 40 refinement levels, but yeah, this is a dynamical range of 2 to the 40 or something, so quite a big number. But in practice, you're more limited. Usually, if you try to reconstruct your grid by the number of digits you have in a double precision number, so eventually you can't really build up your entire simulation again, just because of you're losing the accuracy to match different blocks on different refinement levels together. This is just an announcement to the questions which came up yesterday. So I guess there's very little of motivation why we need gravity on top of the hydrodynamics and magnetohydrodynamics we were talking about and you have heard about. In particular because this workshop is all about star formation and planet formation. So gravity is a necessity and needed force, of course, to form stars and also molecular clouds. Here you see a few examples which we did with the flash code on collapsing cloud cores, even seeing some protostars here, or sync particles, which I will talk about tomorrow, and then a large-scale structure. So we are talking about here of the order of 10 parsec, what you see here on molecular cloud. So this is, of course, this can be only achieved if with gravity, if gravity is included in your simulations. So how is it done in the flash code? So the gravity is actually linked to the hydrodynamics via essentially a source term here via the gravitational acceleration, and the same is true for the energy equation. So in this sense, it is an additional source term. It's not included in the total energy conserving scheme, and in principle, that the total energy should be conserved if you include the gravitational potential, which is, to a certain accuracy it is, but it's not directly implemented in the finite volume scheme here for instance, for solving the Riemann problem. In principle, it could be done, but this is the way so far the flash code uses the gravitational acceleration or gravity. So in a practical sense, where you do find all the modules are essentially in these directories here. So again, in the source structure and the physics comes with that tells you what kind of gravity you want to use, and the particular solver, in particular when it comes down to solving a self-gravitating problem. So you have to solve the Poisson equation. This is done with the help of so-called grid solvers, which solve the Poisson equation, and the directory is given here, where you find all the different solvers, which I will talk about in a minute, essentially. So we have different self-gravity solvers, namely a multipole solver you can use for more spherical problems, and multi-grid solver, particular for Cartesian problems, and a so-called Barnes and Hutz tree algorithm, which also provides you the gravitational potential, but it's done in a different way. So, and of course, there are, external gravitational accelerations you can also include, just because this entire scheme here is done anyway by kind of source term. You can plug in whatever force you like here, and there are three so far implemented forces, and I guess that's very easy to extend if you want to have some other gravitational force, namely a constant force, to maybe simulate something like a Rayleigh-Taylor instability, and plan parallel force which might be useful if you are interested in atmospheres. If you're not going too far away from your surface of your planet or star, that might be a choice here. And of course, there are point masses which might be interested if you are further away from your essentially spherical massive objects. And this is also, the force which is calculated here, the acceleration, this is the same way we also use for particles and zinc particles in the Flash code. Yeah, and then the more interesting, and particularly if it comes down to star formation, the more interesting part is, of course, solving the Poisson equation. So written here, which relates the gravitational potential and the distribution of masses, or a distribution of density. And from there, of course, you can then easily calculate the gravitational acceleration. And as I said, there are different ways to calculate the potential, namely by a so-called multipole solver and multi-grid solver. The multi-grid solver was provided by Paul Ricker already in earlier versions, of course. You see this here with the date of the Flash code. And more or less recently, there's a tree-based and Barnes and Hutz type tree-based solver provided by Richard Wünsch. He resides in Prague. If you have once your gravitational potential here, you just do an finite difference scheme to calculate your gravitational acceleration. So nothing particular fancy. So this is essentially a finite, so a centered finite difference scheme. So it's a second order scheme fitting into the rest of these equations. Yeah, and if you want to test these different solvers, these different Poisson solvers, essentially in your configuration file, which you might have looked already in, you just provide the type of solver you want to have there, either, depending on your problem, of course, either multipole, the multigrid, or the Barnes and Hutz tree, giving these requirements specifically in your configuration file. You also can do this, of course, on the setup command by telling the command line essentially with modules or with physics, and giving these solvers here. So in principle, you know that the Poisson equation is a boundary problem and you have to specify certain boundaries, and these are the boundaries which are supported essentially by the Poisson solvers, by these different methods. Not all of them are, support all of these boundaries which are listed here, namely isolated boundaries. That means, your central object sits essentially in a vacuum, so outside of your simulation box, there's nothing else. Periodic boundaries, that means your mirror, your whatever is in your simulation box to the sides next to it. And then, of course, these classical Dirichlet and Neumann boundaries, so where you either give directly the potential at the boundaries of your simulation box or the normal derivative specifying the Neumann boundaries. I'm not actually sure, and we go through this a little bit, whether this is implemented in any of the solvers, but it's stated here already, and supposedly it shouldn't be a big problem to do this. And of course, you also can give a user-defined plus boundary, so meaning you can provide the gravitational potential there as you like. So now we are essentially going through these different solvers and see what is the basis here of and the differences. And starting with the so-called multipole solver, and the idea is here you can essentially formally solve your Poisson equation with a given Green's function. Here it is given, which you can expand in terms of spherical harmonic functions. So these y's and y stars. So maybe you have seen this. This is a basis for the Green's function, which appears, of course, in the formal solution here. If you just have to integrate over the combination of the density distribution which is given and the Green's function, and then you do have this simulation, then you do have the solution. And because it's a multipole expansion around an radial distance essentially, so so the radial distance comes just from this separation. You also have to define an origin of your problem, and the origin is calculated automatically by the center of mass. So that's given here. So this is always the origin of your coordinate system you're using here is the center of mass. So this, for a spherical problem, it of course makes kind of sense, where you have a spherical mass distribution which most probably peaks at the center. And then, of course, your gravitational potential takes a form like this here. So it's a function of r and so-called source moments, mu of r. And these source moments you can calculate directly from the given density distribution with the Legendre polynomials here, given here. And you do this to a certain order of L, so you're not integrating them to all the multiple moments to infinities. You truncate them, and I think the maximum supported multiple moment is of the order of 10 in the implementation. And of course, the reason is first of all, you use this method only if you have a nearly spherical problem. Of course, if you have a very chaotic distribution of masses, as we have seen in the first slides, and turbulent collapse of a cloud core, for instance, which has many local mass centers, and it's fairly messy in respect of the mass distribution or density distribution. But if you have a more smooth and nearly spherical situation, this is certainly a valid and quite fast method. But eventually, if you deviate from spherical symmetry, you have to add more and more spherical harmonics, so higher order multipoles, and then the problem also scales with the multipole, with the maximum multipole moment squared, which are you using in this setup. So in principle, there is only one major parameter you can use, namely the maximum multipole moment you want to use for your simulation. And of course, the more spherical, the less multipole moments you need. And of course, the higher the multipole moment, the better the solution gets, in particular if you walk away a little bit from spherical symmetry. And then you can also, it supports also what is called a quadrant solution only. So if your system is highly symmetric, so in particular for 2D axisymmetric situation, you only compute your solution for one quadrant instead of the full simulation box, and just copy the results to the other parts. So that, of course, speeds up the simulation quite a bit. And here's the list, essentially, of the supported grid geometries. So it works for 1D spherical, 2D cylindrical, and spherical, and in 3D for Cartesian and axisymmetric setup. Not with, strangely enough, in 3D it doesn't work with spherical coordinates, which I don't know why it is. Maybe it will be implemented eventually. Yeah, if you want to try it, there's a, yes?
What's the difference in 2D? I mean, how do you define spherical in 2D, if not cylindrical?
Oh, that's just the way that essentially, so in cylindrical, you have your radial distance is just in the polar direction, and then you have a set component. Whereas in spherical, you have, in 2D spherical, you have you essentially multiply your radial distance with a cosine of the set coordinate. So it's a different, it's a spherical radius you're using in 2D. It's just a transform of coordinates here. Yeah, there's a test problem in the sense, and I encourage you to work this out based on the Maclaurin spheroid setup. So, and this is used because there's an analytic solution to this density distribution, essentially just a spheroid with constant density. And you can also somehow switch off gravity, meaning you don't have to couple your result. You just calculate the gravitational potential without coupling it to the hydrodynamics. So this is what in this flash setups they call test units. So very simplified setups, essentially just to focus on particular problems. For instance, using the grid solvers. In this case, it's the multipole Poisson solver. Yeah, there's even an improved method I just found essentially in the manual, so I can't say much to it. So but it tells you that it's supposedly much more efficient in the memory layout, and it's also more accurate, as it seems that the multipole solver has some issues if you're essentially using astrophysical distances, coordinates. So if you have run already a flash simulation, the flash usually assumes a so-called CGS unit system, so in centimeters, grams, and seconds. So meaning if you simulate a typical astronomical object, we are talking about at least 10 to the 13 centimeters on an astronomical unit. And there seems to be an issue if you use large numbers with the original version of the multipole moment. Can't say much to this. And it's also the new implementation seems to be more efficient in when it calls subroutine. So it calls essentially a subroutine only once per cell instead of many times. So essentially it should be faster and more accurate. That's the message here. Okay, are there questions to this multipole approach? As I said, so the main idea is here to, if you have a nearly spherical problem, this is your choice here essentially to solve the Poisson equation. Okay, and then we will continue with the so-called multi-grid solver. So this is the, I would say the classical solver which we use for many years. There's a new one by now, but so this is a solver in particular useful for 3D Cartesian problems with a lot of structure in your density. It doesn't assume any symmetry or so. So the one Paul Ricker implemented for the new Flash version, so since Flash 3 and upwards, is based on a method called Greenguard method, and it's slightly different from an older version which used an iterative scheme based on a Gauss-Seidel iteration. But nevertheless, I mean, the main feature is still the same. So it's an iterative solver of the Poisson equation where you essentially propagate your solution in kind of both directions from fine to coarse grid and vice versa. And we talk a little bit about the details here. So you essentially what they call restrict your solution from the fine grid to coarser grids and interpolate the solution backwards from coarser grid to finer grids. And this is called what is called a V cycle, and the reason is because, which is nicely done here in the code by putting in some comments essentially. So it actually looks more like an M rather than a V, but the idea is essentially you do this in your going from essentially coarser to finer grids and check errors, and then do this V cycle again. So as you see here, you do what is called restrict essentially your solution from a fine grid to coarser one, and then you interpolate and solve at the same time the solution, the Poisson equation, and going from coarser to finer grid, and then do it again, and then you check essentially after one cycle your error, which is done by an L2 norm. The main functions essentially you find in this directory here. They're all called gr_hg for Greenguard. So this is how it works a little bit in practice. So these are a couple of definitions which we will use in a second. So we need what is called a residual, essentially the difference between the real solution and the numerical approach solution done here. So you define a residual. Then you need an finite difference operator essentially to do exactly this calculation here. This is just a finite difference operator of the Laplacian here. So this is straightforward, and this is of course added with the. So this is in the x direction, and you add the terms also for the y and z direction. And then you need a restrict operator, meaning you move your potential or solution from finer to coarser grains, and you do this essentially by averaging. And what is meant here, so all these primes, prime indices, these are what is called overlapping indices with the coarser solution here of a given index of a particular grid cell. And you also need the other way around, so the interpolation from coarse to fine grains, fine grids, doing a similar approach and using essentially predefined weights here depending on the direction and the points where you are. And again, so these are the primes are related to overlapping regions with the, in this case, the coarser indices, or the indices of the coarser grid. And here's a little example where you can see how this interpolation works. Essentially, if you have your solution here on the coarse grid marked by the black dots, and you want to find essentially the boundary here on the fine grid, these are the black dots are essentially the values you take to average or to find this boundary, and here are the associated weights. So if this guy here is weighted by 1-1/12 here, and then you have a symmetric weighting here with 7/12, and again this one is weighted also with -12. So you can kind of work out why these weights should have these forms, and then of course this one here next to it is ignored, so it's weighted with a 0. So this is the main idea how you essentially interpolate your solution. So these are the operators we need to do all these multi-grid approach, and then we do essentially a loop, go through different steps here, namely essentially we solve the Poisson equation, and I have written this down here. And in particular, you use again a Green's function, and this is based on a sine approach, or a sine type Green's function. You can read this up a little bit, and if you're interested, the details are also in the manual. And you do this essentially for all levels here. First of all, you ignore, you start with level 0 and ignore all the finer grids, and then you go to the next level and ignore again the finer one, and do this step by step. So you solve your Poisson equation just with one go, and then you compute your residual using the differential operator I defined earlier. So this one here to calculate the residual, and then you essentially prolong, so you interpolate the solution to the child blocks, and take these interpolation then for the next step also as a first try for the solution. And then if you have once your essentially residual, you can check this with a L2 norm, how big is your error essentially, and if you're satisfied with the solution, you can stop the loop. Otherwise, you continue not with the essentially original problem here, but only you solve the Poisson equation using the residual and calculating essentially a residual solution called here, instead of phi, it's called C. And then you add this up to the previously achieved solution here, and then you get a new one, an updated version. And then again, you do an interpolation scheme again, and you essentially continue until you kind of satisfied. So you do these steps here in a loop, and hence it's an iterative method here. So if you're once satisfied, as I said, with the solution, you stop the loop. Yeah, here you see essentially the code of the calls. It's exactly what what is written also in the manual. So you do an iterative solve using residuals, essentially, to find your solution for your gravitational potential. Yeah, and because you need a couple of additional variables to do this iteration step. You not only, so these are the typical variables you need anyway for any other solver, so the gravitational potential and so the actual gravitational potential and the one from the previous time step. So, but you also need 4 more additional three-dimensional variables, if you like. So if you use a three-dimensional simulation, namely the residual you need as a full array, and so are the corrected potential. You also use a variable for it. And to do essentially a periodic problem, you also have to know a little bit about the mass distribution essentially outside of your simulation box. So you have to mirror your mass distribution, and for this you need again 2 more variables for image and for so-called image mass distributions or image potential distributions. So it essentially tells you that it needs a little bit additional memory, at least 4 more variables compared to other methods. Yeah, on this, the solver itself works only in Cartesian coordinates, so in 1, 2, and 3 dimension at least. Don't know, I wrote here twice periodic, so it works for, I think that should be isolated as well, so it works in isolated, periodic, and using the Dirichlet boundary condition. And as I said, the Neumann boundary condition, where you use the normal derivative of your given potential at the boundaries. This is not yet implemented, but it shouldn't be a big issue. So these are the files again. Yeah, here are some results from Paul Rickard's paper about the error propagation with higher and higher resolution. And for a uniform grid, it more or less does what one expects. So the error should scale as essentially as the resolution element squared. So if you increase your resolution element, your error drops. Increase your resolution element by a factor of 2, your error drops by a factor of 4. And this is what essentially is lined out here, and it works fairly well for a uniform grid. So it does exactly what it should do. If you use AMR, your scaling becomes not as perfect anymore, and because you get some errors by the different boundaries between the different size blocks. But this particular example, I think here the finest refinement, the volume of the finest refinement area is only 5%. So this is a fairly small area compared to the rest of the simulation box. So that, of course, can also be improved if you like in choosing a more rigid refinement criterion, for instance. Yes. Oh yeah, E is, so this refers to the Maclaurin spheroid setup, and E is the eccentricity here. So he tested different eccentricities, so this is essentially spherical, and it becomes more and more, cigar type shaped here. So this is essentially the last solver I want to, yeah? Yeah, typically it is slower, but it depends also on the number of multiple moments you use. If you use 10 multiple moments, or more than 5, say, then the multipole solver can be very slow already. So then they start to be more comparable. But if you use really a spherical problem, of course, then you're better off with the multipole solver. But your errors get really bad if you have as I said, a turbulent distribution, essentially, or a fluctuating distribution of densities. Then you essentially can't use the multipole solver anymore, even if it would be faster. But it just produces big errors and not the right result anymore. But it is fairly slow, yeah, the multigrid solver. So there's another solver implemented in the Flash code based on a so-called tree algorithm, which is mainly actually used in SPH simulation, which you might have heard by Paul Clark. So where you essentially are not dealing with a smooth density distribution, you're not directly solving the Poisson equation, you're just essentially adding up masses as you would do in a kind of a Newtonian problem where you have mass distribution instead of a continuous medium. And so this is it's called tree solver. It's based on an octree distribution, and this matches fairly well, of course, with the block-based AMR structure of the Flash code. That's why it kind of it is easy also to implement this particular algorithm in the Flash code, and it should scale or as n log n. So in this respect n means just the number of grid points, essentially the number of mass elements you have, and that should be essentially compared to a direct summation where you have really an n squared problem. You have to, if you want to calculate the acceleration or the force on a single particle, you have to calculate all the contribution from all forces, from all mass points, and hence you get an n squared problem, whereas with this algorithm it should scale as n log n. So far it works only for cubic blocks in the Flash code, and the blocks, that's even more restricted. So the block size, the number of grid points in a block, must be an integer power of 2. And I guess nobody really tested it so far with anything else but 8. So so this is the standard number, and you of course you can try with some other number of grid points. 16, for instance, in principle it should work, but not guaranteed. So this is how it. This is one of the bases how it works. First of all, we essentially additionally to the AMR block, AMR tree block structure, we build or in this algorithm, an additional block tree is generated. So on these essentially 8 grid cells in each direction, you build a hierarchical block by this number here of levels. And of course for 8, that's 3 levels, but starting with the top level 0, top level 0. And then you can calculate for each level essentially the masses and the mass centers. And this is then essentially distributed to all processors. This information, in particular for the level 0 here, and the same is also done in the speaking of the paramesh AMR for the parent blocks. And then this is also distributed to all CPUs, and so each CPU holds the essentially top level tree of this distribution of, and knows all the masses and mass centers. And then, so this is essentially how such a block tree is distributed in memory. It's just a linear array. On each level, it holds 4 informations, namely the mass, and the center of mass, and the coordinates of the center of mass. So for each block, you need not only these 512, but because of the hierarchical level, 804 entries essentially. Of course, we don't want to distribute for all hierarchies, all levels, all the information to all CPUs, because this would kind of violate this idea of that you can use the code in parallel, and it knows only a piece of the entire simulation. So you have to decide which one of the levels of your block trees you want to communicate, and this is done by by choice of a so-called opening angle, and this is a parameter here. And what you do is typically you compare the size of a given node, so depending on the level, of course, with the distance of essentially the block you are looking at. So you loop through all blocks, check within this level 0 tree how what is essentially the opening angle, and compare with your parameter you give, and then build up essentially a communication list which you then communicate to all CPUs. And here's essentially an example. So you first decide which one of the block trees should be communicated to which CPU, of course. Not all CPUs get all the information, but just the one which are really necessary. Namely, it depends on the distance, essentially, of a given block. Here's, for instance, a picture by Richard Wunsch, where you, for instance, if a block is fairly close to the one you are considering right now, you have to communicate essentially all the information up to level 3, whereas if a block is far away, you only have to communicate informations up to level 0. Sorry. So hence, you communicate only really the necessary information here, and this saves, or the idea is, of course, it saves memory and also computational time. And you do this essentially the selection in advance and decide which of the block trees and block level trees should be communicated. And then if you decide it once, you pack everything into a single message for every CPU and communicate and distribute these informations. If you have done this, every CPU has all the information necessary essentially to calculate the gravitational potential. And the main idea is, of course, if masses are far away, you are not talking about the individual masses or mass points there anymore. You collect everything in larger and larger units up to an entire block. And this information is then available on all CPUs, and then what you have to do is essentially what is called walk the tree, so essentially calculate the gravitational potential, and this is essentially what costs most of the computational time, about 90%. But it is, at this point, it is fully parallel. No communication is necessary anymore, because this was done in the previous steps. And then essentially, to get your gravitational potential, or the distribution from each cell, it's added to the gravitational potential for one cell. You again use your angle here, your opening angle criterion, to decide which one you want to add to this gravitational potential here. So you do this in more refined way than before for the communication. So this is done. Here's an example for what is called the parent block. So you compare essentially the size of the parent block with the distance, and always choosing the minimum distance of a given block here, and then add on the cell of the parent block, or the contribution from the cell of the parent block to the gravitational potential of the cell of the block you are considering. And if you're in a leaf block, essentially, so on the lowest level, then you do this essentially point by point for all grid points in your block. But again, using this opening angle criterion to decide which one should be, or at which level should be added to the gravitational potential. So this is essentially this criterion of the opening angle. This is the criterion which essentially speeds up the entire calculation. So you get your n log n scaling. Yeah, here are some examples, again compiled by Richard Wünsch here, on, of course, your simulation, or your quality of the simulation of the solution depends on the opening angle, and the larger the opening angle, the larger typically, of course, the error is, because you sum up more mass points without treating them individually. And then, of course, the smaller your opening angle is, the better your solution is. But of course, it needs much more computing time then. And here's a comparison, actually, of what is called a Bonner-Ebert sphere, so an hydrostatic sphere which has a certain density profile. And he compared this with different solvers here. And so, all the blue region and even the green region goes up to a percentage level of an error. So you can also compute the gravitational potential for the Bonner-Ebert sphere analytically, or at least with a simple numerical integration scheme. And you see how the errors are distributed. They are you get the larger errors here essentially in the center, whereas for the other schemes that's not necessarily the case. So you get a distribution of errors, and the errors become larger, for instance, for the multi-grid method in the outside region. Yeah, that's so far this solver, which can be quite efficient. Again, especially for density distribution, which are highly unstructured, but it is supported only, and in this sense, it kind of is appropriate so far. So it's only supported for 3D Cartesian geometry and nothing else. It can take two types of boundary conditions. On the one hand, isolated, so your whatever blob in your simulation box is surrounded by vacuum, or it can be periodic, But for the periodic case, you need to do additional calculations, essentially, which are called the Ewald field. Values have to be generated up to a certain moment, essentially. And this can take some while, but nevertheless, this has to be done only once at the very beginning of the simulation. And then it can be actually stored in a file and can be read in if you restart your simulation. Otherwise, you have to recalculate these Ewald fields, which I said might take some while. Yeah, and the most important parameter here for the setup is, of course, the opening angle. And this is certainly something I encourage you to play around a little bit, so to get a feeling what is a good value for a certain problem. And yeah, value of 0.5 is certainly already sufficient for most of the problems. And for many times, you can even go up to a value of 1 for the opening angle, which again speeds up your simulation quite a bit. Yeah, all these files related to this algorithm start with GR_BH for the Barnes and Hutt. And yeah, this is essentially the test problem which I all encourage you to try out. The Maclaurin spheroid. Here you see how the setup should look like initially. So that's different projections. So this is, I guess, X and Y, and this is Y and Z here. And in this projection, you see the elongated density structure here. So it's a spheroid which you can, of course, manipulate with your eccentricity. If you set it to 0, you get a sphere. And this is a setup which you might want to try out. And yeah, another setup, maybe there is also what I mentioned earlier, this Bonner-Ebert sphere, so a sphere which has a density profile which can be expressed by a simple differential equation, not analytically, but there's a setup already. But if you want to try out this, you want to update the config file which resides in this directory with the one which I provided here, because there was a little mistake. So you want to first update this before you try the Bonner-Ebert problem. Okay, that's about I want to say about the gravity solver in the Flash for today. Thank you so far. Questions?
Yeah.
Yeah.
Page 3, I didn't get the resolution. That there only can be 8 in cells or grids.
Mm-hmm.
Is that right? You can only have 8.
That's right. In principle, you could have any integer power of 2,
No.
but as I said, nobody tested it so far, so I'm not sure. But in principle, it should work. I mean, of course, then you have more levels here. So you get here essentially 3 levels, plus because of this is given by the essentially the size of your block. In principle, it should work. Maybe you want to try this out there and give me some feedback on this. That's right, yeah. So 8 is for the block size is always a default value. It's a nice number, I guess.